Welcome to the Types of Chemical Bonds video. By the end of this video, you should be able to explain the differences between covalent bonds, ionic bonds, and metallic bonds. You should understand how electronegativity differences determines bond polarity and bond type. And you should be able to identify partial charges on covalent bonds. In order to understand what kind of bonding is taking place, it's important to be able to identify atoms as either metals or nonmetals. So here's a handy refresher. Recall that the metals are generally on the left side of the periodic table. The nonmetals are generally on the right, with the exception of hydrogen, which hangs out over there but is a nonmetal. Let's start with covalent bonding. In a covalent bond, electrons are shared between two atoms. Covalent bonds occur between two nonmetal atoms. So the example here shows an atom of hydrogen bonding to an atom of oxygen. Both of these are nonmetals. And you'll see that a pair of electrons, two electrons, are being shared between the hydrogen and the oxygen. Likewise, there's another bond here because this is water. You have another pair of electrons being shared between that hydrogen and that oxygen. Ionic bonding, on the other hand, occurs when electrons are transferred between atoms. For example, here's an atom of sodium, here's an atom of chlorine. Sodium is transferring one of its electrons to chlorine. This will result in a positive sodium atom and a negative chlorine atom. Those positives and negatives then attract one another electrostatically. This type of bond typically occurs between a metal and a nonmetal. In this case, sodium is our metal and chlorine is our nonmetal. So as you can see in the diagram, here's our metal cations. That's our nucleus and core electrons of the metal atoms. And then we have this sea of electrons that are kind of free floating. Delocalized means they're not trapped in one spot. They can kind of move throughout the substance. Metallic bonding occurs between atoms of the same metal, and it accounts for the unique properties of metals. Recall that metals are said to be both malleable and ductile, meaning they can be hammered into thin sheets or pulled into thin wires. This is a result of the flexibility offered by the sea of electrons model, which allows the metal cations to kind of move around since the electrons are not trapped into place between the atoms as they would be in other types of bonding. They're also good conductors of electricity. Recall that electricity is essentially just the flow of electrons. Since metals have these sort of delocalized electrons, they can flow easily. Now let's zoom in just on ionic and covalent bonds, leaving metallic bonds aside for a while. The type of bond formed between two atoms is largely determined by the electronegativity of the atoms involved. Recall that electronegativity is the degree to which an atom attracts bonded electrons to itself. Let's consider a bond between this red atom here and this blue atom here. Let's make the bond green. Recall that bonds are made up of a pair of electrons, so that green line there represents two electrons, which I'll draw in just to remind us. Now imagine that the red atom has a higher electronegativity than the blue atom. That means the red atom will attract those electrons more strongly to itself. This will result in the red atom being surrounded by more electrons than the blue atom. Therefore, the red atom will have a partial negative charge, and the blue atom will have a partial positive charge. I would call this a polar bond because the electrons are unequally shared. Bond polarity is the measure of how equally or unequally the electrons in a covalent bond are shared, and it's determined by the difference in the electronegativity, as we saw above. The larger the difference in the electronegativity, the more polar the bond becomes. The more strongly the electrons are pulled towards one atom versus another, the greater imbalance of the positive and negative charge, and the more polar the bond becomes. Typically, if you want to think mathematically, an electronegativity difference of greater than 0.4 is considered a polar bond, though these cutoffs are arbitrary and often differ from textbook to textbook. For the purposes of our course, we will consider a CH bond to be nonpolar. Its electronegativity difference is 0.4, which is right on the cusp, but we're going to call that a nonpolar bond. This bond is important to remember because it comes up often. We obviously won't discuss every single individual bond in this video, but the CH bond is really common, and it's important to remember it's considered a nonpolar bond because the electrons are relatively equally shared. Generally speaking, if you get to an electronegativity difference greater than about 1.7, then your sharing becomes so unequal that it's not even a covalent bond anymore. It's actually an ionic bond. Ionic bonds share so unequally that the electrons are actually transferred from one atom to another rather than shared. This will, again, usually occur between a metal and a nonmetal. In that case, again, we don't talk about partial charge. We talk about actual charged ions, a positive ion being attracted to a negative ion. Here's a table summarizing what we just said. We look at the electronegativity differences here. As they increase, we see that the bond becomes more and more polar until it's actually not even sharing electrons anymore. It's actually transferring them and has become ionic. It's important to note that bonding lies on a continuum, meaning we don't typically draw a hard and fast line between ionic bonds and covalent bonds. As the electronegativity difference increases and the sharing of the electrons becomes more and more unequal, we say that a bond becomes more and more ionic and less covalent. Likewise, as the electronegativity difference decreases and it becomes more and more equal sharing of electrons, we will say that the covalent character increases and the ionic character decreases. But it's important to notice that it lies on a continuum, so all bonds have some ionic and covalent character. Zooming in just on covalent bonds for a minute, here's another graphic representing the difference between a polar and a nonpolar covalent bond. This is similar to the image I drew before, but I think it's a nice explanation of what's going on. So what you're looking at here is these two dots are the nuclei of the two bonded atoms, and the blue cloud here is the electrons. Notice here that blue is equally distributed. That represents a nonpolar covalent bond because the electrons are being shared equally. There's no concentration of electrons in any one spot, therefore there's no positive or negative end. Again, this is typically made of atoms with the similar electronegativities. Polar covalent bonds, on the other hand, though, here's this nucleus. Notice that the electrons are not shared equally, right? We have way more electrons on this end than we do on this end. That results in a partial negative charge, which is represented by that symbol here, and a partial positive charge on that atom. This would occur between two atoms with very different electronegativities. When we're talking about covalent bonds, we can't talk about charged atoms because that would be an ion, which exists in an ionic bond. Instead, we talk about partial charge. This is another way of looking at that electron cloud and the resulting charge. When the electron cloud is evenly distributed, as it is here in F2, we don't have any areas of high electron concentration. Therefore, we have a nonpolar bond. However, in more polar bonds here, we see that we have way more electrons on the red side than on the blue side. That results in a partial negative charge on this side and a partial positive charge on this side. Here's a table summarizing everything we just discussed. Recall that the most important thing about bonding is what happens to the electrons. In ionic bonds, they're transferred. In covalent bonds, they're shared. And in metallic bonds, they're a delocalized C. Ionic bonds typically occur between a metal and a nonmetal, and covalent bonds typically occur between two nonmetals. Metallic bonds obviously occur between metal atoms. Ionic bonds will have a large electronegativity difference. Covalent bonds, a small electronegativity difference. Finally, recall that in ionic bonds, atoms actually become charged ions due to the transfer of electrons, whereas in a covalent bond, the electrons aren't fully transferred, they're just shared equally or unequally. The more unequally they're shared, the more the partial charges of each atom will increase. Here's a series of elements and compounds. Pause the video here and try to identify each as ionic, covalent, or metallic. When you come back, I'll reveal the answers. Welcome back. Here's what you should have come up with. Notice I used whether or not the atoms are metals or nonmetals to determine what type of bonding occurs. That brings us to the end of this video. Let's review our goals. First, we looked at the differences between covalent, ionic, and metallic bonds. Then we looked at how electronegativity difference determines bond polarity and bond type. And finally, we identified partial charges on covalent bonds.